Hello everyone. Today we will learn about propagation over water and flat open area. Propagation over water and flat open area. Here we will learn two cases. The first case is land to mobile propagation over water when mobile unit is moving. When mobile unit is moving. Land to mobile propagation over water when mobile unit is moving. And the second case is propagation between two fixed stations over water. These are the two cases we study in the topic propagation over water and flat open area. Clear? Coming to the first case, land to mobile propagation over water when mobile unit is moving. See, this is the fixed antenna station, and this is the moving mobile unit, and this is the over the water or over the sea or over the water. Here we are getting one direct wave from antenna. A direct wave. A direct wave was sent to the mobile unit, moving mobile unit. And here we observe two reflected waves. One reflected wave is that is reflected from the ground surface to the mobile unit. And the second reflected wave is which had reflected from the water or sea water or water. These are the two reflected waves and one direct wave to the moving mobile unit from the antenna. Now we will study this topic. See here, coming to the first point, while studying propagation over water or flat area, it is becoming a big concern. While studying propagation over the water, because it is very easy to interfere with the other cells if we do not make the correct arrangements. What is the reason that the propagation over the water is becoming a big concern and it is easy to interfere with other cells? Here the reason is, we know that the water, the sea water or the fresh water, they are having the permittivities. In general, the permittivities of sea water and fresh water are same, but the conductivities of sea water and fresh water are different. Clear? Here permittivity means the ability of a substance to store electrical energy in an electrical field. The definition I had written here. So when I had considered seawater or fresh water, the permittivities are same, but the conductivities are different for seawater and fresh water. So taking into considerations these points, these permittivities and conductivities, the propagation over the water is becoming a big concern, as it is easy to interfere with the other cells if we do not make the correct arrangements. So coming to the third point, here we will take the path loss calculation. Here the path loss calculation based upon reflection coefficient with a small incident angle of cell site antenna is given as -1. It means the AV value, reflection coefficient, is taken as -1. Now considering these two antennas, one is the cell site antenna and the other is the mobile unit antenna, and both the antennas are above the sea level. See, the cell site antenna is above the sea level and the mobile antenna is also above the sea level. Now we will do the further calculations. Then here what we had observed, there are two reflection points, that is one reflected wave from ground and second reflected wave over the water and a direct wave. So based on this diagram, here see the total received power at mobile unit from two reflected waves and directed wave is given as PR is equal to PT into 1 by 4 pi d by lambda whole square modulus of 1 minus e power j del phi 1 minus e power j del phi 2 whole square. This expression you had already studied in Touré model. The same expression. See, once for reference, I am showing you the Touré model. Coming to the Touré model, see here, the expression PR is equal to P naught into 1 by 4 pi d by lambda whole square 1 plus AV e power j del phi. Here only one reflected wave. So as it is having only one reflected wave, I had written it as e power j del phi, and AV reflection coefficient, it is taken as -1. Now coming to our topic, see here in this diagram, I am having one direct wave and two reflected waves, and I had taken reflection coefficient -1. Then what will be the expression? PR is equal to PT into 1 by 4 pi d by lambda whole square 1 plus AV. Here AV is -1. So I am writing directly 1 minus e power j del phi 1 and minus e power j del phi 2. Here I am writing two times e power j del phi 1 e power j del phi 2. Why I am writing del phi 1 and del phi 2? Because I am having two reflected waves. One reflected wave from ground to the mobile unit and second from water to the mobile unit. As I am having two reflected waves and the direct wave, I am writing 1 minus e power j del phi 1 minus e power j del phi 2. And I had taken reflection coefficient AB is equal to -1. So I had written directly 1 minus e power j del phi 1 and e power j del phi 2 whole square. We know that PT is the transmitted power, D is the distance between two stations in the diagram, and lambda is the wavelength. Here del phi 1 and del phi 2 represents the path length difference between direct wave and two reflected waves respectively. While studying the Touré model also we had studied. There we had written 1 minus e power j del phi 1. Only one, there exists only one reflected wave. So we had written only 1 minus e power j del phi 1, and we had written as del phi 1 as the path difference. Del phi is a phase difference between direct wave and reflected wave. There we had written in Touré model. But now coming to this expression, we had written two times 1 minus e power j del phi 1 and e power minus j del phi 2, and del phi 1 and del phi 2 are the path length difference between direct wave and two reflected waves respectively. Now coming to the next step, here del phi 1 and del phi 2 path length difference between direct wave and reflected waves are taken less than 1 for land to mobile propagation over the water. This is the direct step we had written. So over land to mobile propagation over the water, here del phi 1 and del phi 2 are taken less than 1. If I had taken it as less than 1, then the final expression I will get is PR is equal to PT into 1 by 4 pi d by lambda whole square. This is the final expression for land to mobile propagation over water when the mobile unit is moving. This is the final expression. And here last in the 8th point, I had given you a conclusion point. You have to remember that is the path loss for land to mobile propagation over land is 40 dB per decay. Path loss for land to mobile propagation over water is 20 dB per decay, and for free space is 20 dB per decay. Okay, this is the first case. Okay, thank you.